Head HOD, Civil Engineering Department, and one of the coordinators of this FDP for the welcome speech. Ma'am.
Thank you, Amu. Respected Principal, Dr. P. Sojan, Dean Planning and Development, who is a professor in the Civil Engineering Department also, Dr. Solly George, dear participants and my dear colleagues. A very warm good morning to one and all. It's my pleasure to welcome all of you to the 3-day faculty development program on sustainable building materials and practices organized by the Department of Civil Engineering, MBITS, conducted on digital platform in line with the social distancing norms of COVID-19 pandemic. We are proud to announce that this FDP is being sponsored by APJ Abdul Kalam Technological University, who consistently supporting these kind of programs very much. This is for the second time the Department of Civil Engineering is conducting a KTU sponsored FDP. The modern construction industry is torn between satisfying the demands of clients and the responsibility to ensure that we don't indelibly damage the planet that sustains us all. The objective of this program is to make the faculty of engineering colleges more conversant of the sustainable practices in the building construction, which will be benefited by the budding engineers. We hope that this FDP would help the participants expand their knowledge in the area of sustainable construction practices, which will be shared to your students. Moving on to my duty. Welcome all of you to this 3-day program. Today, we have the chief guest of the inaugural function, Dr. N.V. Ramana, the Honorable Director of NIT Warangal, who will be joining us shortly. Due to some important engagements, he has informed us that he could not join now, and he will join by 10 o'clock only. Also, he will be the presenter for today's first session. We are very thankful to Dr. N.V. Ramana, who is constantly associating with many of the activities of MBITS and who is a great academician too. In spite of his absence, on behalf of all those who present here, I wholeheartedly welcome Dr. N.V. Ramana to this program. We have the president of this inaugural function, who is the patron of this FDP, Dr. P. Sojan, our beloved principal here. Sir has been the pillar of support for all the programs and academic activities conducted in our institute for past several years. Thank you for all your guidance, sir, and very happily sharing with all the participants about his great achievement of awarding the Principal of the Year 2021 during the 7th Higher Education Summit ceremony for his outstanding and exemplary contribution towards education, skill development, and research. Congratulations to you, sir, and on behalf of all those who present here, proudly welcoming you to this program. As you all know, we have the eminent resource persons from reputed institutions like IITs and NITs and many construction industries who will be joining with us on the coming 3-day session. Very warmly welcoming all of them to this program. Dr. Solly George, Dean Planning and Development of MBITS and one of the professors of the Civil Engineering Department is present here. She is a well-known academician having vast experience in teaching and retired as the principal of MA College of Engineering, Padamangalam. Dr. Solly is a constant motivator for us and acknowledging all her support for the coordination of this program. A warm welcome to you, ma'am. We are very happy to see the overwhelming responses from the faculty of various engineering colleges for participating in the FDP. We have selected 60 participants from various KTU affiliated institutions on the first come first serve basis. And the participants are representing from different 15 colleges. I wish all of you a very fruitful sessions on the coming 3 days, and I am sure you and your students will be benefited by this FDP very much. With great pleasure, I welcome all of you to this program. No need to welcome my dear colleagues on this occasion. They all need big congratulations for contributing to organize such a program very well. Thank you all for your support. On behalf of all those who are present here, I welcome all my colleagues to this program. Once again, welcoming all to this program. Attain greater knowledge, stay safe from COVID-19 pandemic. Have a nice day. Thank you.
Thank you, ma'am. Now, we will have a brief detailing about all the sessions included in this FTP. And for that, let me call Ms. Veena Jayakrishnan, Assistant Professor, Civil Engineering Department. Veena, please.
Respected Principal, Dean, Head of the Department, faculty members, and dear participants, a very good morning to one and all. While the pandemic still continues to disrupt normal operations, we continue to maintain normalcy as much as possible. We all have moved many of our regular trainings and activities online, which was the case for this APJ Abdul Kalam Technological University sponsored 3-day faculty development program also on the topic Sustainable Building Materials and Practices. Today, the job assigned to me is to give a brief report or detail on the program. The main objective of this faculty development program is to introduce the participants to the world of sustainable building materials and give an insight into how and where it can be used. As everything is at its core now, the issue of a clean environment is a matter of public health. Each day, we will have 3 sessions, 2 sessions in the forenoon and 1 session in the afternoon. Each session will be handled by professors or industry personals from reputed institutions and industry. After the inaugural ceremony, we will start the first session by the chief guest, Dr. N.V. Ramana Rao, the Honorable Director, NIT Warangal. He has promised to enlighten us on the topic recent advances in concrete and sustainable materials. After each session, the participants may interact with the speakers. They may unmute and ask their queries or may type their questions in the chat box. Today's second session will be handled by Dr. B.B. Das, Associate Professor, NIT Surathkal, on the topic Hydration and Microstructure Properties of Nanosilica Admixed Sustainable Cementitious Mortar. At sharp 2 p.m., we will start with the third session by Dr. T.I. Eldo, Professor, IIT Bombay, who will discuss on the topic Sustainable Water Management through Waste Water Recycling and Conservation. With that, we hope to conclude day 1 of our FDP. Second day also, we will start at 9:30 sharp with the talk by Dr. Anil Joseph, Managing Director of Geostructurals Private Limited, Kochi. He will take us through the sustainable innovations in construction industry. He is one of the most desired structural engineer experts in India with almost 28 years of experience in this field. After that, next session will be handled by Engineer Shankar N. Menon, Director, Seed Engineering Consultants and Academy, Kochi. He is a senior member of Seed Design and Management team with 54 years of professional experience in planning, design, and execution of engineering projects in its mechanical disciplines. He will be talking about the importance of sustainability in modern building industry. Second day will be concluded by the talk on green synthesis of artificial aggregates and structural applications by Dr. T. Palanisamy, who is currently working as Assistant Professor in the Department of Civil Engineering at National Institute of Technology, Karnataka, Surathkal, India. All the participants, please note, at the end of day 1 and day 2, there will be a quiz based on the talks on that day. We will be sharing the Google quiz link in our WhatsApp group after 1 hour of the third session. Kindly attend the quiz and the participant who gets the highest score will receive a cash award of ₹1,000. Final day of the program will be handled by 3 eminent resource persons. First session is on a systematic framework for pre-treatment of sugarcane bagasse ash and its utilization in cement-based products by Dr. Prakash Nandagopal, who is currently working as Associate Professor at IIT Bombay. Second session is by Dr. Job Thomas, Professor at Cochin University of Science and Technology on the topic Sustainability Index Evaluation of Building Materials. Last but not the least, the final session will be handled by Dr. Elson John, Associate Professor of MA College of Engineering, Kodamangalam, who will be discussing on the topic more sustainable concrete technology through the effective use of admixtures, which will be followed by the validatory function. We hope to keep up with this time schedule and request all participants to be on time for each session. I would also like to take this opportunity to thank all the participants for showing interest in this FTP. We are pleased to see the overwhelming response. We have got around 60 participants for this FTP, and I'm sure by these 3 days, all of us will attain greater knowledge and understanding about the subject and will definitely get benefited. E-certificate will be provided to all participants. For that, I request all of them to fill the feedback form, which will be available in the chat box after each talk. With these few points, I would like to wish each one of you a fruitful 3 days with us and stay safe and healthy. Thank you.
Thank you, Veena. The backbone of MBITS, Dr. P. Sojan, who has more than 30 years of blended experiences with major international petroleum companies in the Middle East and premier educational institutions in India. He has more than 70 publications and guided 5 PhD aspirants. He co-authored 6 textbooks and has many international awards and recognitions. Recently, he was awarded the Principal of the Year 2021 by Center for Education Growth and Research, New Delhi. Let me invite our beloved principal, Dr. P. Sojan, for the presidential address for this ceremony. Sir.
Good morning to all of you. Am I audible?
Yes, sir, you are.
Yeah, very warm good morning to all of you. Respected Honorable Director of NIT Warangal, Professor N.V. Ramana sir, and our head of the departments, faculty members, and respected participants for these 3 days FDP sponsored by Kerala Technical University. It's with immense pleasure today we started this program with this inaugural ceremony, and I'm sure that as you have seen that the panel members from the various IITs and NITs and the major engineering fields who are practicing into the field will enlighten you with abundant knowledge in this particular domain. And also I am very thankful for the MBITS, particularly Civil Engineering Department, for completing all the formalities with the KTU, as well as for hosting this 3 days FDP in this manner. Also, our special appreciation and thankfulness to this KTU for sponsoring this event. And also, probably you must be knowing that MBITS is the only college which was selected during 2021 under the New Code of Education Award 2021. And out of the 25 institutions in the country, among all the universities, deemed universities, IITs, NITs, and the premier institutions, 25 institutes were listed listed by this new Code of Education, and MBITS is the only institute from Kerala for representing that. It was happened because the continuous improvement methods which has been adopted, particularly during the COVID pandemic, using the digital medias and all. And during the last years, MBITS was fortunate to conduct a series of webinars and FTPs with a total number of 12,000 plus participants from 1,800 institutions in India and abroad. And also, I'm very thankful for all the faculty members, all the associates, and all other institutions who jointly participated in this venture. And this journey, we are continuing in this FDP in this year also. I wish that all these participants will be benefitable. And we also promise that the quality will be maintained, and also requesting all the participants to be available throughout the session, so that as per the university norms also, we'll be issuing the certificate only if you are attending the sessions completely. And I wish that this is just not for the paper, and this will be very much useful for you for the practicing. And this is something which you can relate with the new education policy also, where you will expand your skills and knowledge in the domain of expertise which you are looking for there. I wish that this is a grand success, and thank you very much for organizing this, and all the best, and have a nice time and enjoy the time in the virtual environment for the coming next 3 days. Thank you, all the best.
Thank you, sir. Dr. Solly George, Dean, Planning and Development of MBITS. She is retired as principal from Mar Athanasius College of Engineering, Kodamangalam, and has 33 years of professional experience. She did her BTech in Civil Engineering from MAIS, Kodamangalam, MTech in Geotechnical Engineering from IIT Madras, and PhD from Cochin University of Science and Technology. Her area of interest is geotechnical engineering, environmental geotechnique, and solid waste management and ground improvement. Let me invite Dr. Solly George for delivering the felicitation. Ma'am, please.
Thank you, Ammu. Am I audible?
Yes, ma'am.
Good morning, one and all. Respected Chief Guest of the function, Dr. N.V. Ramana Rao, the Director of NIT Warangal, President of the function and backbone of MBITS, Principal Dr. P. Sojan, HOD and one of the coordinators of the FDP, Mrs. Manju George, and the other coordinator, Mrs. Dept, HODs, Dean, participants, and my colleagues. I'm so happy to be in this inaugural function of the KTU sponsored FDP, being organized by the Department of Civil Engineering in the emerging area of sustainable building materials. In the COVID pandemic scenario also, the department is organizing this FDP in a perfect manner with the full support of the principal and the cooperation and the support of the department as well as the faculty from other departments. I take this opportunity to congratulate the whole department for coordinating this sponsored FDP from KTU. And also, I take this opportunity to congratulate the coordinators for bringing eminent resource persons from the prestigious institutions like IIT Bombay, NIT Warangal, NIT Surathkal, KUSAT, MAIS, and we can see. I'm also happy that two of my students are also the resource person. One from IIT Bombay, Professor Eldo TA, and the second one, Professor Elson John from MA College of Engineering. We are closely associated with, and I know many of the resource persons who are engaging the classes. Thank you all for being with us in this FDP. Then we have experienced resource persons from industry, like as Manju was mentioning, Professor Anil Joseph, and the second industry also. And I'm sure all the participants will be benefited and enriched by the various sessions handled by these eminent personalities. I wish all the best for the smooth and perfect conduct of the FDP, and I wish all the participants 3-day fruitful sessions with the online platform and engagement with the online engagement with the MBITS. I wish all the success once again. Thank you all. Over to you, Ammu. Hello.
Thank you, ma'am.
Ramana Rao sir will join at 10:10.
Oh, okay, 10:10, sir. Okay, sir. There is a small announcement for the participants. We are conducting a Google quiz on today and tomorrow's session at the end of the final session. So all the participants kindly attend that. For that, the link will be shared to your WhatsApp group, and the top scorer will get a cash prize of 1,000. Now let's see a small video on sustainability. Let's share the video.
Are we missing the sound? Are we missing the sound?
Yes, sir. Paisley is working on it.
Architecture materials. Although concrete is a core component in homes, public buildings, and bridges, it's not the most sustainable building material out there. Commercial concrete production releases tons of greenhouse gases into the atmosphere every year, contributing to environmental pollution and climate change. Fortunately, there are more sustainable construction materials that present a greener alternative to concrete in both residential and commercial projects. 1. Straw bales. Straw bale building is a nod to the days when we built our homes from natural and locally sourced materials. Instead of relying on technology and manufactured materials, we use what the earth provides. Straw bales are used to replace concrete, plaster, gypsum, and other building materials and walls. When sealed properly, they have a high insulating ability. As a renewable resource, straw is both sustainable and affordable. 2. Bamboo. The recent popularity of bamboo amenities such as furniture and utensils may make it seem trendy, but it has been used in construction for millennia. Its combination of lightweight, tensile strength, and renewability make it an ideal replacement for expensive imported materials and an alternative to rebar and concrete construction, especially in areas with easy access to locally sourced bamboo. 3. Recycled plastic. Plastic is emerging as one of the more sustainable construction materials. Instead of sourcing, mining and milling new components, researchers are producing concrete made from ground-up trash and recycled plastics. This practice reduces greenhouse gas emissions and provides a positive new use for plastic waste that would otherwise be clogging landfills. 4. Wood. Wood, a tried-and-true construction mainstay, retains many advantages over concrete, steel, and other industrial building materials. Trees absorb CO2 as they grow and don't need to undergo energy-intensive procedures to be converted into a construction product. When a forest is properly managed, it is also renewable, resulting in a biodiverse habitat. 5. Rammed earth. Another natural technology, rammed earth has been used by human civilization for thousands of years. Not only does it last a long time, when pressed tightly in wooden forms, it creates walls that have a similar feel to concrete. The rammed earth buildings being produced today can be fortified by bamboo or rebar for added safety, and mechanical tampers cut down on the labor needed to produce sturdy walls. 6. Ferric. A newer building material, ferric uses a wide range of recycled materials, such as steel dust, to create a building material that resembles concrete but is actually even stronger. In addition, this innovative material absorbs and seals carbon dioxide as part of the drying and hardening procedure. Ferric is therefore not only less CO2 involved than concrete, it is also carbon neutral. 7. Timbercrete. An intriguing material composed of concrete and sawdust, timbercrete is lighter than concrete, and the sawdust component both recycles a waste material and replaces some of the more energy-involved ingredients in traditional concrete. It also reduces transportation emissions. Timbercrete can be shaped into pavers, blocks, and bricks, making it both versatile and sustainable.
Dr. N.B. Ramana Rao, the director of NIT Warangal since 2017. He did his BE in Civil Engineering from Osmania and MTech from IIT Delhi. Dr. Rao has been awarded the 1989 Commonwealth Scholarship to pursue PhD in Structural Engineering and 1998 Commonwealth Fellowship to pursue postdoctoral research in Civil and Structural Engineering at the University of Wales, UK. He has edited 3 books and published 137 papers in national and international journals and conferences. He has guided more than 50 MTechs, 8 PhDs, and presently guiding more. He has been recognized by different awards like Outstanding Concrete Engineer Award by Indian Concrete Institute, Sir Arthur Cotton Memorial Prize by the Institution of Engineers, India, State Best Teacher Award by the Government of Andhra Pradesh, Best Designer Award by Indian Concrete Institute, and Young Engineer Award by the Government of Andhra Pradesh and Institution of Engineers, India, Andhra Pradesh State Center. Dr. N.V. Ramana Rao has been an expert committee member constituted by UGC for grant of autonomous state to various technical institutions, a member of the committee to frame affiliation guidelines for engineering colleges by the Government of Telangana and AICTE inspection committees. He has held membership of several important high-power committees constituted by the Government of Andhra Pradesh and Telangana. He has been a member of the Academic Senate and Board of Studies Chairman in Civil Engineering, JNT University, Hyderabad, past Chairman and Secretary of the Indian Concrete Institute, Andhra Pradesh, Hyderabad Center, an Executive Member of the Indian Institute of Bridge Engineers, and an external expert member of ISRO Departmental Promotion Committee. With this brief introduction and with immense pleasure, let me invite Dr. N.V. Ramana Rao for the inaugural address. Sir, please.
Please allow me to share the screen.
So you can please share.
Okay.
Good morning, sir.
Yeah, good morning. I'm just sharing, yeah.
Good morning, sir. Please go ahead, sir.
Is my screen visible?
I have some network issues. You may please continue, sir.
You have the screen visible? Can you?
Yeah, screen is visible, sir. Yes, screen is visible. You may inaugurate the session and please continue, sir.
Sir, you are not audible. Please unmute yourself.
Sorry, yeah. Okay. Okay, am I audible now?
Yes, sir. Yes,
yes,
sir. Now it is audible.
Sorry. I think there was some, I don't know why it got, yeah. So I would like to, and my screen is also visible, no?
Yes, sir.
Oh, yeah. So thank you for inviting me for this webinar on sustainable building materials and practices being organized by MBITS Kerala. Professor Sojan Lal, the principal of the institute, is very passionate about organizing several webinars, and I'm glad that he has organized this one also. And I would like to thank Ms. Manju George, Head of Civil Engineering Department, Mrs. Veena, Jayakrishnan, Assistant Professor Civil Engineering Department, apart from our principal, Dr. P. Sujan Lal, Dr. Solly George, Dean Planning and Development, and Ms. Dept Varke, the coordinator of this FDP. And also, I understand that this is also sponsored by the APJ Abdul Kalam Technological University. So this 3-day online faculty development program. So mine will be the first lecture. So I'll directly go to the lecture. It will be about 1. What's the duration of my lecture, madam?
So 1
so
hour, sir. You can take more than that.
Okay. So the title is this one. Recent advances in concrete and sustainable material. And So as usual, I request you to kindly, in case you're doing through mobile, you can put that, otherwise put mute and all that. And any questions, I'll take it in the chat box, so that I request all of us to kindly mute. So when we say the sustainability, the word, I think many people are confused. So let us first define what is sustainability. Sustainability can be defined as the development that meets the needs of the present without compromising the ability of the future generation to meet their own needs. So this is an international definition. So very nicely, we have to also make ourselves satisfied. We should not be having too much greed or waste the resources. And we should also make sure that the future generation also, their needs are also satisfied. Otherwise, they'll curse us. They'll spoil their opportunities. In fact, coming to the concrete, because we are all civil engineers, and this is one thing which is the most widely used material and consumes a great amount of resources. So this is, a lot of research has gone on how we can make concrete as a more sustainable material. In fact, contemporary concrete typically contains about 60 to 20% of cementitious material, about 6 to 8% of mixing water, about 60 to 70% of aggregate, and about 2 to 3% of admixture by mass. So this is how it is done. So why concrete is not sustainable? The main problem with concrete is not sustainable. The reason is in cement manufacturing, the whole process of, because cement is an important ingredient of concrete. In cement manufacturing, limestone has to be decomposed as limestone. This is the equation. Calcium carbonate at 1000 degrees centigrade breaks into calcium oxide and carbon dioxide. So if 100 units of limestone is burned, you get 56 of calcium oxide and 44 is carbon dioxide. So 1 ton of cement contains 620 kgs of calcium oxide, and hence almost 487 kgs of carbon dioxide is emitted. So which is a polluting agency. It creates a lot of pollution to the environment and other things. And the carbon dioxide, in addition to this, carbon dioxide is also produced from fuel burning during the current production, cement production. In fact, the amount is from 320 kgs to about 450 kgs and depends on the advances of the burning technique. So why concrete is not sustainable? Because it requires mining of limestone, mining of other things, processing, and then transporting. All these processes involve emission of carbon dioxide, and that is what makes it very difficult for it to be sustainable. So the challenge before, billions of tons of raw materials are needed for cement manufacturing, and all this process requires a lot of electricity, heat, and other things. So it uses considerable amount of energy, and it will adversely affect the ecology of virgin lands. A large amount of carbon dioxide is produced in all the above operations. And today, if you see, there's a huge consumption of natural resources. It has a great impact on the environment. If not well controlled, definitely compromise the ability of future generation to meet their own needs. So the consideration on sustainability of concrete may contain 3 aspects. First is how to reduce gas emission, especially carbon dioxide emissions. Second, how to reduce your energy consumption. So these are the challenges, as a young engineers, we should be able to address these challenges. Definitely you can make a difference to the whole thing. So therefore, I request that, you will have to address these issues as engineers, and how to reduce the raw materials consumption from natural resources, because you are actually excavating a lot of natural resources and spoiling things. A lot of construction application. When you see any construction site, how difficult it is. This is the problem. So how to reduce the raw materials consumption from natural resources during production, construction, application of concrete. So I'll show you a small video to define what I mean by sustainable concrete, and then you can. Is it audible? Sound is coming?
Portland cement-based concrete has proven its value as the most versatile, durable, and storm-resistant building material available to the construction marketplace. However, Portland cement concrete's impact on our environment is significant. In 2013 alone, concrete required global cement production of 3.6 billion metric tons, accounting for 5% of global man-made carbon dioxide emissions. Given concrete's popularity for strength, durability and economy, cement production will continue to raise annual carbon emissions to an estimated 6 billion metric tons by 2050. This enormous environmental burden is under mounting scrutiny, with many asking, how can society leverage the many benefits of concrete while significantly reducing the environmental impact of Portland cement production? The most widely accepted solution lies in the expanded use of supplementary, alternative, cementitious materials, such as fly ash, slag cement, and silica fume, as partial or total replacements for Portland cement. For the past 10 years, Ceratec, an American company based in Baltimore, Maryland, has been conducting extensive research and development with the goal of creating a sustainable cement using only fly ash, a byproduct generated by electrical utilities. Ceratec has successfully commercialized a 100% Portland cement replacement, comprised of 95% fly ash and 5% rapidly renewable liquid additives. Ceratec's innovative cement technology provides a leadership path for an industry that has a mandate to become more environmentally responsible. If Ceratec cement were used to replace all Portland cement, it would produce the following immediate and profound environmental benefits in just 1 year. Man-made CO2 emissions would be reduced by 3.6 billion metric tons, or the equivalent of removing 688 million cars from the world's highways. That is all of the cars in the United States and over half the remaining cars on the planet. 237 billion gallons of fresh water would be saved, equal to the volume of water that flows over Niagara Falls in 3.5 days. 5,000 terawatt-hours of energy would be conserved, a sufficient amount of electrical energy to power the entire city of Las Vegas for over 100 years. 5.4 billion metric tons of virgin mineral resources would be preserved, while 3.6 billion metric tons of waste would be diverted from our landfills, enough to bury the entire city of Washington, D.C. under over 34 feet of limestone and 52 feet of waste material. The extended durability and longevity of concrete produced with Ceratec cement would compound these already impressive environmental benefits by a staggering 3 to 4 times. Within the foreseeable future, it would not be practical nor possible to replace all Portland cement concrete. However, replacing even a small percentage of Portland cement with Ceratec cement would provide tremendous environmental benefits for everyone on the planet. Ceratec's cement technology has been thoroughly validated by internationally recognized researchers, independent laboratories, and government testing facilities. The environmental benefits of Ceratec's Ecomax brand concrete has been independently verified with the most rigorous of independent environmental audits, the Environmental Product Declaration. Ceratec cement meets ASTM C1157 standards as a high sulfate-resistant hydraulic cement for inclusion in building standards and constructions codes. Ceratec cement concrete is stronger and more durable than Portland cement concrete and is suitable for any application where Portland cement concrete is typically utilized. Concrete produced with Ceratec cement uses standard batching practices and requires no special equipment or methods to place and finish. Customers to date include the U.S. Department of Defense, various state departments of transportation, industrial manufacturers, port authorities, and municipalities. All of these customers have one thing in common. They require cost-effective, exceptionally strong and durable concrete, while valuing the benefits of sustainable materials. Forward-thinking architects, engineers, government planners, and corporations are driving the transition to sustainable built environments through significant reductions in the carbon footprint of building materials. This commitment to environmental stewardship can now be built upon Ceratec cement concrete, the lowest carbon footprint concrete in the world. To determine the environmental benefits that could be realized by using Ceratec.
So you have seen this video which tells brief history why this sustainability is very, very important for all of us. Now, coming to the thing, what are the solutions for sustainability? First thing is how to make concrete more sustainable. The three methods of achieving sustainability of concretes are reduce, reuse, and recycle. These are common thing in any environment. So it should be emphasized that as more and more concrete structures age, more and more demolished concrete will be produced if it cannot be recycled and reused. In fact, recycling, reusing is something very, very important. The deposition of the construction waste will cause another environmental problem. So the other important thing is the construction waste that is coming out because of demolition or because of construction will lead to another environmental problem. So now, for sustainability, people are made aggregate recycle from demolished concretes are usually more porous and weak. Hence, it is important to develop some technique to overcome the problem and ensure that the quality of the concrete is made up of recycled aggregates. So let us see the hierarchy of construction and demolition waste management. So first thing is reduce, reuse, which I already told you. Recycle, recovery, and landfill. So this is the most favored option. Now this construction and demolition waste, many times you are demolishing the old buildings and building new buildings, so that requires a lot of things, and you will find that this management is very, very important. So the moment we say construction waste, what is it? So as per the definition, if you see, is unwanted materials generated during construction processes. For example, demolished concrete fragments, brick pieces, wood, plastic waste, etc. So how can you reuse? The process of using a material again for same or a different function, for example, using coarse aggregate, can we reuse at all? Is the issue. So you can use coarse aggregate obtained from concrete waste for preparation of textile. It is possible and research has gone. And when we say recycling, the process of converting waste materials into new ones for reduction of waste of potentially useful materials. So when you actually demolish a building, you will find that there are different types of activities like renovation, rehabilitation, and the wastes are. So renovation 40%, demolition 50%, and new construction 10%. All these activities create construction and demolition waste. So if you see construction and demolition waste, it includes waste comprising of building material debris and rubble resulting from construction, remodeling, renovation, repair, and demolition of any civil engineering structure. So why demolition? Because the structures during period of time they age and they cannot actually live beyond more that. So that is a problem which many of the buildings have actually. Similarly, unsafe constructions, they will collapse, so that will generate demolition waste. The waste created from non-engineered poor quality construction, and then poor quality construction and maintenance. All these things are leading to, like earthquakes, a lot of demolition waste comes out, and what to do with it. And all this is a lot of concern for environment. All this is leading to a lot of. So let us see what are the issues for environmental concern. So here you see that sand is being actually excavated from the river beds. So there's a lot of activists who says don't bury the issue of sand mining. A lot of restrictions have been put by governments now for sand mining. So this is something very, very important for all of us to realize that sand mining is something which is going to cause a lot of danger. So let us see the necessity of processing the construction waste. You will find, disposal of this waste has emerged as a problem. How do you dispose it? You can't dispose it. In fact, there is an estimate that India is presently generating construction demolition waste to tune of 23.75 million tons, yet no disposal method is being practiced in 70% of the industry because of the easy availability. Because the new material is easily available, nobody disposes, just throws them here and there. As you go in your cities, you will find a lot of dump yards, So due to unlimited use of aggregates, the extinction of naturally occurring materials like rock will soon take place, and due to this, the application of reusing and recycling of waste material. So we are trying to justify why we need to reuse, why we need to recycle. Why only concrete? There are several materials. So let me first clarify that concrete, when you say, it is the most commonly used construction material, almost 1 ton for every man on the earth, okay? So you can imagine how many tons are being used. And aggregates in that concrete are used for very specific purposes. Typically, they make up about 60 to 70% of the volume of a concrete mixture. It is the least expensive of the materials used in the concrete. So the economic impact is quite significant, in fact. Now, compared to other comparable building material, concrete is less costly to produce and remains extremely affordable. That is the reason why there has been extensive use of concrete. In fact, sometimes the concrete material has to be demolished during ongoing or old construction. The concrete waste obtained from these processes is called demolished concrete. It is a very common type of waste generated during pile foundation, precasting, etc. So what does this C&D waste consist of? See, the C&D waste consists of, you can see in this picture, you can also notice it consists of concrete, brick, timber. What else you can see? So concrete, brick, timber, sanitary glass, steel, and plastics. So how do you reprocess? So first, a building is there. So just identify structures consisting of concrete and structures consisting of different building materials, demolish, processing it, and then crush, sand, use, and then concrete rubber. So steps involved are collection of construction scrap from the site, classify them according to their properties, send them to the separation and treatment plant, differentiating the compound, that is the aggregates, treating them, and finally reusing them for construction fresh concrete. So what to do? First, you store at the source. Appropriate storage space is required, which is very difficult in cities. Segregate them, then what else? And then what do you do? There are many processes for recycling, and however, the best procedure adopted is collection of waste from the site, transporting to the recycle unit, initial crushing and sieving, and then final crushing and grinding, and then forwarding it to the construction unit. So many times, you do mechanical sorting of these aggregates, and you will notice that as we are doing mechanical sorting, there is a bar screening that is there. Then there is a magnetic separation. So magnets, they will attract the steel parts. Then air classifiers. So this is how you got a sand. It's called a recycled sand. It's quite good, very good properties, but the process involves a lot of equipment and energy. That's why people are not using it. But future we have to use that. And let us see the property of this recycled aggregate. Coming to the particle size distribution, the sieve analysis is done after crushing and sieving as per IS code that it separates out and very satisfactory. Recycled aggregate meets all the standard requirements of natural aggregate. So nothing to worry about it. The specific gravity and water absorption, yes, specific gravity, saturated surface, dry condition of recycled concrete. These properties are very much essential if you want to do a concrete design and a concrete mix. So this is something which we have to use and do for ourselves. So the sorting process, let us see, all these equipments are required. There is a chemical and mineralogical appraisal, and then there is a mechanical sorting. So in these aggregates, if you make study, you will find the water absorption ranges slightly higher, 3.0 to 7.4, which is slightly higher than natural aggregate. The modulus of velocity, which is actually control the reflection. Recycled concrete aggregate has a lower NCA up to 15% only. It can be increased if hardened concrete paste adhere to the aggregate and are removed well. Coming to the compressive strength, the average compressive strength, normally cubes are cast and determined as per IS 516. And natural aggregate age 1, 3, 7, 14 are tested for properties. And generally, there is a reduction in strength of only 2.14, which is not much, and we can easily accept it. Coming to the crushing and impact values, as per IS 2000, the crushing and impact values for concrete bearing surface should not exceed 45%, 50%. So all these aggregate reused from construction waste satisfies many of the requirements. But what are the challenges in the Indian context? So for recycled aggregate to be used in greater quantities, you will find that in a country like India, there are certain aspects that need to be taken care of initially. First is the setting up of a proper institutional mechanism for taking care of all the steps such as collection of construction and demolition waste. Transportation and disposal is a key of key importance. Outsourcing of such functions to private enterprise is an idea that the concerned authorities could give a thought to this day and age of open economics. Setup of the necessary processing infrastructure, and necessary infrastructure should also be available for testing the quality of recycled aggregates. Project developers need to be educated as on-site waste management plans, and the concerned authorities need to plan an awareness campaign using the electronic and online media to promote the virtues of recycled aggregates and removing misconception about recycled aggregate as being of inferior quality among the public. So this is a big building, and you will see that the Indian real estate market is expected to go very, very high. So construction demolition waste is going to increase. And therefore, we have to think ways and means of using these recycled and cycled aggregates. We have to conserve the diminishing natural aggregate, so then only you can make it sustainable. And you have to see new ways of using construction waste and protection from environment. It's economical, creating additional benefit, avoids excessive land filling. Many times what happens, these waste are dumped in the land. So land filling is there and spoils the whole agricultural characteristics of the land. So what are the disadvantages? Why is it not so popular? Let us understand. You will find today there's a lot of inexperience with recycled aggregate products due to lack of exposure still remains a surmountable barrier to the recycled concrete market. Water pollution can also happen during recycling process and still not feasible in all sites and requires heavy machinery and equipment. So reuse, you can do it. Reuse, deconstruction means a planned selective demolition in which salvage, reuse, and recycling of demolished structure is maximized. So this is, you see, this is a structure and a lot of material is generated now. How do you reuse it? So the recycling plants are there and they're recycling, getting good aggregates. So the Pollution Control Board guidelines given by the CPWD give us the guidelines recommend pollution mitigation in operation of dump sites and processing facility, mainly for bulk generators in cities and towns. So every city has got a pollution control board and they have set up guidelines, but nobody follows. So let us see this, how we can actually recycle it, and then we will proceed.
But the idyllic landscape is under threat. Local construction firms have their eyes set on the Jura limestone. It forms the foundation of the Swabian Alb. And several million tons of it are disappearing each year. Large trucks transport the stone to a nearby gravel plant. Gravel is an important raw material for the production of concrete, and large quantities of concrete are in great demand in a region known for its dynamic construction sector. There are more than 40 stone quarries in the Swabian Alp alone. Many more throughout the state of Swabia, and hundreds in the other central German uplands. Additional gravel pits located along major rivers like the Rhine, Donau, Main, Weser, and Oder provide even more of the coveted material to the construction industry. As a result, some 4 hectares of gravel are dug up or blasted away every day in Germany. Each year, that equals the area of a small German town with more than 10,000 inhabitants. It's an enormous use of natural resources. In addition, most construction takes place in high-density urban areas, while most gravel pits and quarries are located far outside the cities. Trucks transport millions of tons of stone along German roads to construction sites in the cities. This form of raw material procurement not only takes its toll on the landscape, it also leads to higher energy consumption. But the raw materials are closer than we think. German cities are full of them. Many structures in Germany were built sometime between the 1950s and the 1980s, and they're mostly made of concrete. They'll have to be renovated from the ground up in the coming years, and many of the interiors will have to be modernized to meet current needs. The fact is, many buildings are in dire need of renovation, and some are ready to be demolished. Take this foundation structure of a former factory building in the south of Stuttgart. A hydraulic chisel breaks up concrete and masonry on location. An excavator dumps the material into a crusher. The crusher processes the parts into recycling material with a particle size of up to 60 millimeters. A screening unit then separates the gravel into various particle sizes. The recycled concrete can be used as the frost-resistant material FSS 045, forming the foundation of this future parking lot. The problem is, concrete recycled from old buildings will have to be used in the construction of new buildings in order to increase the total proportion of recycled materials. And that's important for the conservation of natural resources. The principle is put into practice at the recycling center of the Fes Erdbau Company in Kirchheim-Teck. A variety of concrete and building rubble materials are processed for reuse here, covering an area of 30,000 square meters. The rubble is collected within a radius of 15 to 20 kilometers from the recycling plant. Since the material can be sorted here according to type, only pure concrete ends up in the crusher. A magnetic belt removes the steel reinforcements. The result is a clean fraction with a size of 2 to 16 millimeters. Nearby concrete factories use this material to replace the gravel from stone quarries or gravel pits, saving natural resources. The Swabian building material experts also process masonry and even roofing tiles. Using a special screener located in the bucket of a wheel loader, material can be separated from plaster remains, small particles of wood, and sheeting. The resulting fraction also makes its way through the crusher and into the recycled concrete. Because of its careful gathering and perfect sorting, Fes is able to recycle 80 to 90% of the demolition waste. That's around 1/3 more than usual. One buyer of the recycled aggregate is the Mineralogical Frischbeton concrete manufacturer. Located just a few kilometers from the recycling center, the company uses the so-called recyclate for the production of fresh concrete. It procures scrap concrete from a variety of suppliers in the Stuttgart area. A bucket conveyor lifts the recycled rubble into the concrete factory's storage area. There, other chambers contain different aggregate materials used for the concrete, including natural and crushed sand and a fraction of shell limestone chippings. The mixing device combines these primary raw materials with the recycled secondary materials. Then comes cement, water, and the construction chemicals required by the recyclate. Current guidelines allow up to 45% of the mixture to contain processed concrete rubble. The resulting product is a recycled concrete that meets the industry's quality standards and technical demands. Normal concrete mixing trucks deliver it to the nearest construction site. It has the same viscosity as normal concrete, making it just as easy to use as the conventional material. And it's just as resilient. Guidelines require a so-called strength class of C3037. Weaker classes are also admissible for mild frost and acid exposure. Recycled concrete has been widely accepted on the market. Customers are satisfied with the quality. It's almost the same as conventional concrete, and it's allowed us to save 30% on primary raw materials. The new material is further tested in a laboratory at the Krieger Group in Neckar-Rems. The engineers hope to increase the 45% maximum proportion of recyclate currently allowed in concrete. They're preparing a so-called compressive strength test. A sample cube with an aggregate of nearly 100% concrete rubble is positioned in the device. Then pressure is slowly applied. The currently admissible strength class requires the sample cube to withstand a force of well over 700 kilonewtons. That equals the weight of more than 60 mid-sized cars. The test shows that recycled concrete made of 100% recyclate can withstand the required strain. That means it could contain twice as much concrete rubble as previously allowed by law. Engineers are carrying out additional tests with recycled concrete samples in the lab's cold chamber. These tests indicate that recycled concrete is far more resistant to frost and de-icing salts than previously thought by lawmakers. The state of Rheinland-Pfalz has a research project aimed at changing current regulations to substantially increase the amount of recycled aggregates used in concrete. It's also aimed at processing all the materials found in construction waste in order to reuse them in further construction. That would create a closed cycle of materials within the construction industry. The first building that used recycled concrete was constructed in Rheinland-Pfalz. Along with Berlin and Baden-Württemberg, the state plays a leading role in the use of environmentally friendly building materials. Recycled concrete has long been found in buildings like this housing complex in the Swabian town of Winnenden, and in the foundation of this arched bridge in neighboring Backnang. Examples from Switzerland demonstrate that recycled building materials can also be used in large-scale construction projects. And recycled concrete is shown to possess many more capabilities than current legal guidelines suggest. That could substantially increase the proportion of rubble used in building materials. And that, in turn, would protect the environment in several ways. First, the demolition, processing, concrete manufacturing, and use of recycled building materials all takes place locally. The shorter distances that need to be traveled decrease the impact of material transport on the environment, also requiring far less energy than used to be the case. And since more construction waste is recycled, less storage space is needed. In addition, the less gravel and crushed rock that is removed, the more one valuable resource can be preserved: the landscape.
Okay, so this shows recyclable concrete, how it can be done. And so there a lot of scientific utilization of more industry waste is now required for making our planet sustainable. In fact, let us see the scientific utilization of some of the raw materials in the industry. So one way to make concrete sustainable is to utilize industry waste or byproducts to replace the raw materials for making concrete, such as cement and aggregates. The industry byproducts utilized to replace cement are usually called supplementary cementitious materials. Examples are blast furnace slag, fly ash, limestone powders, and silica fume, which are the most commonly used SCMs, that is supplementary cementitious materials. So recycle in concrete, how can you do? Concrete industry also recycles the waste products of the electric and steel industries as substitutes of virgin raw materials of concrete industries, thereby reducing the environmental impact of both. Moreover, these supplementary cementitious materials contain reactive silica that can react with CH in concrete to form secondary CSH and to improve concrete properties. Due to the incorporation of SCM in concrete, the structure of the concrete at the nanometer and micrometer levels become more complex. So why not use OPC? See, why we are using this blast furnace or cement? It is the most consumed commodity in the world after water. It's also most energy intensive material. A lot of energy is required to manufacture it. The cement production leads to high carbon dioxide emission, which is the cause for the high carbon dioxide emission, and it is causing pollution to the environment. In fact, almost 1 ton of carbon dioxide is produced for every ton of cement, including transportation, everything. So it is produced by calcination of limestone. I showed you the equation, and you will find. So alternative methods are, for sand, you can replace with manufactured sand or recycled glass aggregates, or all these things are good replacement to sand, and you can save a lot of materials. In fact, a lot of tests have been carried out in the laboratory, and you get wonderful results. So one system along this is alkali activated cementitious material, in which geopolymer and alkaline activated slags are two good examples. And then a new high belite cement was developed currently in China. They are using it, but China has been quite doing intensive research. Now we are also doing. So the energy consumption is one which is cause of concern. So comparison, carbon dioxide, let us see. So you see in the cement, the C3 and the CS, and you will find that carbon dioxide is maximum for the C3S. So therefore, we have to make changes in the chemical composition to improve the sustainability. So a new concrete has come, which is called as geopolymer concrete. The answer is why geopolymer concrete? Because it utilizes waste materials from industries such as fly ash, silica, fume, and CGBS. It protects water bodies from contamination due to fly ash disposal and conserves acres of land that would have been used for coal combustion products disposal. Produces a more durable infrastructure. And geopolymer is a very eco-friendly construction material. It is used as a replacement of cement concrete. In geopolymer concrete, cement is not used as a binding material, but fly ash, silica film, or CGBS is used as a binding material. It is an innovative material that is characterized by long chain networks of inorganic molecules, and it is a potential alternative to the conventional Portland cement. So this is given a good opportunity thing that you find. So you have a fly ash, and then it adds to fine aggregate, which adds to the coarse aggregate, and then you get a good concrete. This is called as geopolymer concrete, and this is how it is made. And you will find the coarse aggregate. We have fine aggregate, and then admixtures, and then alkaline activators. So all these are required for producing the geopolymer concrete. Let us see a small video how you can make geo. So what are the material used? Fly ash, which is easily available in thermal power plants. And then coarse aggregate is available, reused, recycled, and all that. You require fine aggregates, you require sodium hydroxide. This is very important. And then you can get it to the properties that you want. You can design it, and nicely you can control it. We have ground granulated is another industry byproduct. So it's a mineral admixture of silicates and eliminates of Ca and other bases. It has same main chemical constituents as OPC. It improves the compressive strength of GPC. And this is a table. And you see these activators, and you will find why is it called geopolymer? Because the following things, geopolymers are polymer is there. So are cementitious materials that do not require the presence of cement to harden or gain strength. So they are finding replacement to cement because we realize cement is generating a lot of carbon dioxide, which is not desirable. And how are they formed? They are formed as a 3D network of silicon and alumina material, and this is how the chemistry looks like it. So then you have got ash, you require some solution, you get a nice thing, and you get a good cement. And a lot of testing can be done, and you will notice that these polymers are very good in terms of the properties, and they can almost replace cement. Compressive strength is also good, and durability is good. So this is how you actually manufacture and test in the lab. So this is in our lab at NIT Warangal, where we are testing all this and getting results, samples and all that. We get good results. Then we plot the graph. The compressive strength, you see, as time goes, it is increasing and stabilizes, and very good. Chemical resistance also is very good and very durable. So there's no danger, especially in coastal areas. We have done creep test also, and that also is doing very well. So all the properties are very good, because before using, you have to test the properties. Coming to the drying shrinkage, you will find that shrinkage also is very favorable for this, and is not. You can use it confidently. You can use it in construction. Compressive strength is also very good, almost comparable with the regular cements. And then it has got very high aggregate content, and you can really do wonderful results. You will get, and other things are the elasticity properties. So without testing these properties, you cannot arrive at any of the solution. Therefore, you have to test all these properties like Poisson's ratio, E value, and you find that it is almost comparison with the ordinary Portland cement. So if you replace the ordinary Portland cement with these industrial waste, you are creating a sustainable environment. So that is what it is. The properties also, I told you, is very good, nothing to worry. And also, you have another advantage is that chemically also it is very stable. And you see in global warming, this is how it is. In fact, the sustainability issues are, today, because of pollution and the greenhouse effects of industrial and all that, is actual production of cement is contributing to 13.5 billion tons of carbon dioxide per year. And then you find geopolymer, which is made out of waste, is helping us to improve the footprint and reduce the carbon footprint, which is very good. It is very sustainable, and Portland cement and fly ash is very good, and you have so much things being generated throughout the world and America, and where we have now sustainable lagoons and all these things. So this has really made life very simple for engineers, and we are able to do the testing and other things and get good results with geopolymer concrete. And we did a lot of microscopic examination also, and you see how the binding is done. How you can see these parts of geopolymer and then steel reinforcement. How well it is bonded, which is a good thing, and aggregate. And then behavior of at elevated temperature also excellent behavior is there. Bond strength is also very high, and about 1/3 of its composition 4 times OPC. So let us see a quick video on this, and then we'll try to conclude because time is over.
Imagine what concrete as a building material has done for us as a society. It keeps our feet dry and gives millions of people a roof above their heads. However, the concrete industry is the second largest producer of CO2 and is responsible for emitting up to 5% of global CO2 emissions. At the same time, there's a fast increase of waste production in many other industries. At the Faculty of Civil Engineering and Geosciences, the Geocon team is working on a new type of concrete that uses waste and byproducts instead of cement.
This is an example of the geopolymer concrete. It is made by mixing different industrial byproducts, then activating the products by alkaline solution. We get a binder that bind aggregate, and finally we get such a hardened material that has comparable or even better properties than the traditional concrete.
The Geocon group is doing fundamental research on the geopolymer material. First, the waste products are characterized. Then, through microstructure development, properties and performances of the material can be predicted. The research outcomes enable the team to set up design possibilities and put these into practice.
We are also trying to demonstrate how this material works in practice. So we started with non-structural applications such as casting the pavement tiles, 3D printing complicated shapes, toward the structural applications. The first one was the geopolymer canoe last year. This year, reinforced cantilever bench. And in the near future, we will cast the geopolymer bridge.
If we can put geopolymers into practice in the Netherlands, the complete production of concrete can be done without importing resources. In addition to this, we would need less landfill space in the Netherlands because we can make use of waste and industrial byproducts. By using geopolymer concrete, we are not only reducing global CO2 emissions, it also makes us rethink the role of waste. Geopolymer concrete might just be the building material of the future.
So this has a lot of future, especially for a country like us, and I think it is going to take away and make concrete more sustainable. And coming to applications, you have seen in the video also, it can be used in pavements also, it can be used for making tanks, and also it can be used for making roads, pavements, blocks. It can be used almost for any application, even high-rise buildings also it can be made. For dam construction also it has been very popular because it's very, so the future is very good and bright for us. It can be used as paver blocks. A lot of construction has already happened, so that is the beauty of it, and you will really appreciate that you can bend it to a shape that you want, and then a lot of advantages are there because you've got high compressive strength, high tensile strength, low creep. I showed you all the tests that we conducted, and we realized that these are so many advantages that we are having. Height dwell, and it's even fireproof, so that is one good thing that you have. In fact, the disadvantage is also there. It is difficult to create, pre-mix only, and then require special handling chemicals like sodium hydroxide and other things. And then other things have to be done. So I would like to conclude my lecture by saying that concrete can be made sustainable by using less energy in production and producing less carbon dioxide than normal concrete. Usually carbon dioxide is present in the cement and aggregate, and suitable replacement can be found. And today, cheaper and efficient and better performing system are now available. Geopolymer concrete is a very promising construction material due to its low carbon dioxide emission. So high early strength, low creep and shrinkage, acid resistance, all this is being very good. And there's a widespread application in precast industries, which is a future of construction. Today, less breakage is there during transportation and enhanced research and other things. And it should emphasize more and more concrete structure age and more demolished concrete will produce. So we have to make use of recycled and reused concrete to save our environment and our future generation. So questions, let me see in the chat box if there are any questions. So the chat box says, sir, the session was informative. Can you give an idea how widespread? Yeah, recycled aggregate is now getting popular, and especially in the government construction. CPWD has come out with a manual, and they are very happy with the success. Only thing is the processing requires additional costs, so that the builders are not willing to bear. But in areas where there's a sand shortage or wherever there's aggregate shortage, they are doing it. In areas where there's no shortage, still they are using the old color. Very informative, very good session, very relevant. The next question is centralized recycling units factories under government. Yes, some of the factories are under government, some of them private also are set up. A lot of profit is there, because wherever there's a shortage, they can, sand shortage is a common thing, especially in coastal areas and areas where sand mining is prohibited. Then Manju George says, can we use any type of demolition method? See, demolition has to be done in a systematic way, because otherwise, you will be just spoiling the things. Bricks can be recovered, the steel rods can be recovered, and other things. So it has to be done in a systematic and a proper way. So I see no questions. There is one student, Assistant Professor Jobly, raised hand. So what is the question you can ask?
So if you have any questions, you can raise.
Sir, am I audible?
Yeah.
Sir, we have a lot of reservoirs in our state, Kerala. And now the government is trying to desilt the reservoirs because the capacity of the reservoirs have now they cannot store that much water. So the desilting process is going to take place for all the reservoirs. So can we utilize this silt for fine aggregate as fine aggregate by some process?
Yeah, fine aggregate, but you have to see the chemical composition, number one. Number two, you have to see the grain size. If it meets the requirements of IS 238-6, then definitely you can use it. There is one more question from Binoy Roy Georgi saying, how do recycle aggregate prices compare? In fact, recycle is just slightly cheaper because, only thing is sometimes, it's not very cheap. So therefore, still people use the normal aggregate, but in the coming years, it's going to become very, very cheap. Yeah. So thank you, Sojan Lal, and thank you very much. Since I have another meeting, so I had to hurry up.
Yeah, thank you very much, sir. In spite of so much busy schedule, and also we know that Professor Jayakumar sir's work, and again, in spite of all the challenges inside the campus, we are agreed to this, and the continuous motivation was. And on behalf of the entire MBITS family, again, the new Board of Education, which have been not successful unless you have very strong support from you, sir. We are always acknowledging your all continuous support unconditionally. And once again, thank you, sir, for being with us. Thank you, sir.
Thank you. Let me allow to leave.
Okay, sir. Thank you. Hope that was really interesting and informative session. All the participants have enjoyed the talk and benefited a lot. E-certificate will be provided to all participants. For that, I request all the participants to fill the feedback form in the chat box. Now, I would like to invite Assistant Professor Fasif P. Samath, NGM College of Engineering and Pharmaceutical Science, Malappuram, to give a small feedback on this session. So please.
Good morning to everyone. Am I audible?
Yes.
Okay, it's very informative session. I'm very thankful to our great resource person, Mr. Ramana Rao sir. And I'm also very thankful to the team of Department of Civil Engineering, the MBITS College. It's very informative and very to know about the recycled concrete, to know more about that knowledge. Okay, thank you. Thank you to all the behind this FDP.
Thank you. Kind attention, participants. On the basis of today's 3 sessions, A Google quiz will be conducted, but not soon after the end of the session, like within an hour span. The link for Google quiz will be sent to the WhatsApp group so that all can participate. Likewise, tomorrow also Google quiz will be there. The top scorer of both days will get a cash prize of ₹1,000. So kindly participate. Now, let's take a break for 10 minutes. We'll start the next session sharp by 11:15 a.m. Thank you.
Sir, good morning.
Yes, sir. Good morning.
Good morning, sir. Sir, you are audible, very much audible.
Yeah, I can hear you.
Okay, sir.
Can you hear me?
I can hear, sir. Very much clear. Sound is very much clear. The first session just it have ended just now.
Yeah, that's right.
So next session 11:15.
Actually, can you give me the access of actually I joined into one in my
now.
can you allow access? Okay, like, for example, I am seeing my laptop, I'm able to access. But here in the computer, I'm unable to like share my screen actually.
Okay, sir. We'll give permission, sir. Now, 1 minute.
Yeah.
Sir, we are working on it, sir. Just a minute, sir.
Okay, okay, fine.
So what is the other name, sir? The name of the system?
Yeah, I'm just 1 minute. I have just made as a Dr. Baby Das.
Now it's okay, sir. Now it's okay.
Yeah.
Now can you access, sir?
1 minute. Yeah, now it is possible. Yes. Yeah, now I think you can able to see my screen.
Sir, very much, sir. Clear.
Yeah. So just okay. I think another 5 minutes we will start.
Definitely, sir. After 5 minutes. Actually, we have asked them to join at 11:15.
Yeah.
Just check.
So just let me know when we will start. Okay.
11:15, sir. 11:15.
Yeah. Fine. Okay.
Are you in Bhubaneswar, sir? Or
no, I am in NITK Surathkal only.
okay, sir.
Yeah.
Welcome back, participants, to the first day of 3 days online faculty development program on sustainable building materials and practices sponsored by APJ Abdul Kalam Technological University. For the second session, we have got an eminent speaker, Dr. Vibhuti Bhushan Das, who is currently serving as an associate professor at National Institute of Technology, Karnataka, Surathkal, India. His research interests include design and development of sustainable construction and building materials, microstructure and durability of concrete, construction planning and practices. Dr. Das has handled a number of research projects sponsored from Department of Science and Technology, Government of India, Royal Academy of Engineering, UK, Kudramukh Iron Ore Company Limited, Mangalore Refinery, and Petrochemicals Limited. The fund generation and research contributions have led to the development of Sustainable Construction and Building Materials Laboratory at NITK Surathkal, a specialized lab that practices the theme of sustainability. He has published over 150 papers in journals and conferences and has given several keynote presentations across the world. He has guided 4 doctoral students and more than 70 master's theses. Currently, he has 8 students who are doing their doctoral thesis and around 15 students having their master's degree. He has been serving as a postdoctoral research associate from Center for Innovative Material Research, Lawrence Technological University, Southfield, Michigan, USA, and has obtained Doctorate of Philosophy from IIT Bombay, India. He has won a number of awards, one of the prestigious being the Outstanding Reviewer Award from Construction and Building Materials Journal elsewhere. He has edited a number of books entitled Sustainable Construction and Building Materials, Select Proceedings of ICS CBM 2018, Recent Developments in Sustainable Infrastructure, Select Proceedings of ICSRDI 2019, Smart Technologies for Sustainable Development, Select Proceedings of SMTS 2019, Recent Trends in Civil Engineering, Select Proceedings of TMSF 2019, and has been serving as one of the guest editor of Indian Concrete Journal, June 2019 issue and December 2020 issue, and is on the editorial panel of some of the reputed construction, engineering, and materials journals. With this brief introduction, I would like to invite Dr. B.B. Das to deliver his talk on the topic, Hydration and Microstructure Properties of Nanosilica Admixed Sustainable Cementitious Mortar. Over to you, sir.
Thank you so much. And good morning to all of you. Good morning to the organizing team, the head of the department, the principal of the institute, and all the participants, students, if anybody is there, and also the special thanks to Mr. Jobil who initiated the correspondence with me. So today I'm going to discuss, or I will say I am going to talk about one of our specialized or you can say one of the advanced research that we are doing on the hydration and microstructure properties of a Nanosilica Admixed Sustainable Cementitious Mortar. Well, we all know how with time the addition of nanoparticles is keep on gaining the attention in the cementitious composites. But still, we are unable to make it as one of the basic ingredients of concrete, because there are a number of disadvantages, number of challenges to the industry, to the researchers, to the academicians. So, but still, how we are going to make it sustainable? So that is the actually key. And across the world, a lot of research is going on this particular field. So the key is here when we talk about a cementitious material or a cementitious composite. Remember, the key things we need to understand is the hydration as well as the durability properties, or you can say the microstructure properties. And that is the key actually at this point of time. Well, I have seen in the many, okay, like research is going on, but and many, okay, like many of the like papers when I edit, okay, like as a Springer books and all, I see many authors say, sir, our papers got rejected. But remember, only working on the basic engineering properties is not going to give you the solution, because you will say my concrete is very much, okay, very much having high strength, but may not be having sufficient, okay, durable. So that is the where you are failing. And if you don't report the microstructure properties, or you are unable to define how your material is durable, well, it is not going to give a sense at this point of time, at this, okay, age. So that's why, like, when we go ahead with any cementitious material or any kind of foreign material, there, okay, like you have to go with the understand how this material is getting along with your composite, with getting along with your cementitious ingredients or ingredients of concrete. So that is the key here. So I will just, okay, like go ahead in this way, like how we have started the work. Actually, this is one of my PhD scholars' work, and there are good number of publications in this particular field also. So I will briefly like cover the introduction of concrete. We know well, okay, like the concrete consists of certain ingredients like cement, aggregates, and the water. And the key thing here is the hydration, or the products that are getting generated, or the hydration products that I get. That is the key here. So what is the amount of your calcium silicate hydrate, and what is the amount of your calcium hydroxide? Formation is going to play the role for your cementitious composites. So we know actually, I don't want to go into the equations. Okay, we have already studied, okay, the in concrete technology, like, but I would say when my hydrates, okay, when I'm going to the like the hydrate phase, okay, of the material, well, I need to identify what is the things within my matrix or within my system. So if you come to the right side of the picture, these are actually the cement particles before the hydration reaction, or you can say the no water, like just, okay, when the ingredients are in the dry stage, the moment we add water, you can see the second picture is showing, okay, like there is a coating, okay, actually on the ingredients. That is, you can say it's basically the hydration products precipitates on the surface of cement particles. And here we will say, like, I will assume like all hydration process happen, but you know, and we all know concrete is a composite material. The white patches that you see is basically the pores, and that is inevitable. You cannot, okay, avoid pores in concrete or in the cementitious materials. Well, what we are doing actually, what is the next generation of we started using the pozzolanic materials, the pozzolaners. What is a pozzolana? Well, the pozzolana we know is a material which, when comes in contact with water and the calcium hydroxide, it starts to form the hydration product, or the final hydration product, that is calcium silicate hydrates. So examples like GGBAs, fly ash, they all are the pozzolanic materials. So why you are using it? Why you are using the pozzolanous in the concrete and the cementitious composite? Well, to reduce, we are trying, okay, we are trying, or efforts are being made to reduce the pores within hydration products. So we are trying to minimize the pores. So well, there are certain phenomena. We know the pozzolanic reactivity, the pozzolanic activity index, many things are there actually. And then your particle size of the pozzolan will matter, the specific surface area matter, the reactivity will matter. Those are the things that actually I'm not going to cover here. But so you can see the next, okay, like I will go into the how, okay, just for idea, you can see like now when I'm dealing with my structure, okay, we are just talking about the performance in a 10 to the power minus 0 meter actually. So I will say the 1 meter. Always we are discussing about per meter, okay, length of the beam, okay, per meter length of the design. But if you see who is controlling actually, well, I have the aggregates, which is okay 10 to the power minus 2, fine aggregates, and the cement, which is okay like which is of 10 to the minus 6 micron. The gel, okay, like that is being developed, okay, that is comes into the like 10 to the power of again of still lesser. Then when I'm coming to the silicate, that hydrates, it comes to 10 to the power minus 9. But you cannot believe, like we are discussing about the hydration, that is calcium silicate hydrates. But actually, okay, scientists have proved it is the molecules that is defining, okay, the properties of the engineering properties for a meter scale of the specimen. So what is the key here? Well, the key here is understand this part. Try to understand this part of the chemistry, because this part is a labor's job, not okay scientist or engineer's job, because this is what okay, we are doing. But if you understand this chemistry, you can really control the performance in this of the scale. So that is the key here. That is what I am going to talk about in this part. Okay, mostly the calcium silicate hydrate, micron to nano scale I am going to discuss. So if you see the history of concrete, well, 19th century, okay, we started about normal concrete. 1960s, okay, like high strength concrete. We know already, like most of the developed countries, particularly United States, the Europe, they all got developed, okay, like in 1960s, 60 onwards. So Japan, okay. So those are the countries. Okay, excuse me. Hello. Okay, I think there is some disturbance. Okay, I will go ahead. So next is the nano-based concrete. The present scenario is the nanoparticles admixed concrete. Now, what is the nano concrete? Well, the nano ingredients with at least one dimension of nanometer in size. So that is what we call as a nano concrete. Then what is the nanoparticles? Well, the nanoparticles is clustering of atoms and molecules in the range of 1 to 100 nanometer. 1 to 100 nanometer. Now, what are the advantages? Advantages is superior surface to volume ratio, excellent surface morphology. Now, what is the, like, for example, human hair is 5 orders of magnitude larger than the nanomaterial. So 5 times, okay, hair is 5 times the size for nanoparticles. So you can see here, like what is the scale? Okay, I had shown there the same scale. But normally we discuss about, when we talk about nanoscience, we talk about this, what is my nanoscience. So if I define nanotechnology dealing with nanoparticles, that is one of the dimensions in nanometers or 10 to power minus 9 meter. Scientists are defining this is a new era of technology, utilizing the intensively small things, leading to the extraordinary behavior in the properties of the materials. Well, if you can able to deal with a nanoparticle, remember, your performance is going.
Sir, you can switch on the mic once again.
Now you can hear me?
Sir, clear, sir.
Yeah. So it is going to give you the extraordinary behavior. But remember, dealing with intensively small things is not an easy job. All right. So that is what, okay, that is the what we are facing at this point, the problems in dealing with the nanoparticles in the cementitious compound. Well, if you go into the more actually like how, okay, like researchers, like see, the research is being carried out for last of the 20-25 years of the nanoparticles research. If you see, a lot of papers are there, but still there is need of more research actually. Now, what like researchers have suggested, well, ability to control or manipulate materials at the atomic scale. If you are adding nanoparticles, there will be atomic scale manipulations. Imagine that is the what, okay, like is the advantage of it for adding nanoparticles. It improves the material's bulk properties, mechanical properties, durability and sustainability, and volume stability. Also, the lower levels of environmental contamination. So, I mean, the aggressivity of ions which attacks to the concrete is going to be very much less actually, because the porosity is going to be lesser and lesser. Now, when you talk about like when how nanoparticles is acting, okay, with the cementitious composite. Now, there is a beautiful picture given by Thomas et al. 2009. It's a beautiful, okay, paper actually, like it is called as the topochemical reaction. So, like means how, okay, like the nanoparticles independently working and filling the pores. Now you can see here. Now see, this is your the cement, and this is what your is actual hydration process. When we talk about ordinary Portland cement. Now you will get here. These are red color is your hydration product. Remember that is my calcium silicate hydrates mostly, and the white one is your pores. And remember that is mostly my capillary porosity. And what is capillary porosity? Well, the capillary porosity is the amount of formation of calcium hydroxide, which is going to be responsible for the generation, okay, or formation of capillary porosity. So you can see here, this is the red one is my hydration products. Well, these are still unreacted. Okay, this gray color is still unreacted particles. Now come to the C picture. Now here I have added some nanoparticles. Now you can see here there are seeds. That each nanoparticle started acting, okay, in the hydration process so fast, it independent of the particles. It's starting, okay, as a seed. And you can see here almost, okay, like the formation of hydrogen products is quite high, and the porosity is much less. Right? So that is the advantage of when we add nanoparticles in the cementitious compound. Okay, well, when we talk about the nanoparticles, there are many actually. Okay, there are many like which like are available in the market also. But the first nanomaterial that replaced microsilica is the nano SiO2, Nanosilica. Like if you see, okay, if you search, okay, in the Google, okay, like people are working on the nano Fu2O3, nano TiO2, titanium dioxide, okay, nano, okay, like copper, okay, like, so there are many, okay, varieties of particles are available. But for cementitious material, because we need the silica, our material is calcium and silica rich, so we need silica. The more of calcium rich. So what we are doing, we are just, okay, like looking for a silica based material. So nanosilica is being preferred by the cement chemists, the concrete technologists. So if you see the market size, like, well, particles are available from 500 to 650 nanometers with spherical morphology. But depends on the cost. If you go into the low size, like suppose you say, I need a 5 nanometer particles. So the manufacturer is going to charge you definitely more, okay, cost if you go with the 500 nanometer particles. So that is the, okay, cost. If you go smaller and smaller, you have to pay more and more. So that is the point where you have to optimize which particle size is going to be used for your cement matrix. That is also one of the key. Well, this, okay, this is a, like, whatever I spoke, actually, this is a tabular representation on, okay, like influence of nanosilica on concrete properties. Like I will say, like it acts in two ways. One is highly pozzolanic, very much, okay, reactive, highly pozzolanic. And second is, it is acting like a wonderful filler. So all the voids are getting filled by the particles. Okay. So whatever I told, or actually other things is same actually. So now what is the, like, problem actually? What is the problem? Well, remember, we are acting a size of 10 to the power minus 9 meter. So smaller particle size, what is the problem for us? For a concrete technologist, for a civil engineer, is the drying shrinkage. Is one of the biggest challenges. Is a drying shrinkage. Autogenous shrinkage, thereby developing a large number of cracks in concrete. So what is the, like, what is the, like, mitigating, like, method? Well, you have to go for a intensive curing methods, which is practically not feasible. That's why when you speak about nanoparticles to the construction manager, the field engineer, they will say, no, sir, okay, it's very difficult for us to deal with the material. Because it is going to induce a lot of drying shrinkage. So you have to cure it properly, cure it efficiently, then there will not be any problem. Because we have tested in the lab and did a lot of, okay, like, mock test also. If you are curing it properly, there is not going to be any kind of drying shrinkage. Second is the non-economical. Well, it is definitely, okay, a costly metal, I will tell you. Third is high heat of hydration. We have a smaller particle size, so definitely going to be the hydration process going to be very fast. The reactivity going to be very fast. So the heat of hydration production is going to be very high. Fourth is the slump loss. Because of the heat of, like, high heat of hydration, and because the smaller size of particles, water consumption is going to be more. So means you necessarily, okay, need a super plasticizer. Without a super plasticizer, you cannot, okay, work with nanoparticles. So these are certain, okay, number of disadvantages where the construction managers, where we civil engineers are unable to bring to a larger scale, okay, to the fields, the usage of nanoparticles, okay, in the fields. Now, what is the need actually? Well, the need is use of secondary cementitious materials in conjunction with nanosilica. Well, we know, and we have dealt very successfully the secondary cementitious materials or the pozzolanic materials, the fly ash, the GGBS, the silica fume, the rhizoscas, the bagaces, all kind of secondary cementitious material we have dealt it very good at, and we have the experience. So now what have to do actually? But the consumption, the blending. So the blending of nanoparticles with secondary cementitious materials is going to give us a solution, okay, a sustainable solutions. Now we know also, like we know also, like the challenge is how to blend. What amount of material you are going to blend. When I talk about the plain concrete, the question is coming actually whether I will add fly ash, cement, or the fly ash, cement and nanoparticles, or maybe the fly ash, like ultrafine fly ash, then nano like fly ash or the nano SiO2, then okay, cement. So this question is coming, okay, in a larger way, or you can say in technical way whether it is going to be binary or ternary or maybe a quaternary. So point is the selection of right combination of material plays a vital role. So so when we did a lot of research, when we realized this is one of the biggest challenge, okay, like unless you are going to adapt some mathematical model. So the key here is the thing is a thorough knowledge and understanding of the raw materials and their basic properties is very much essential. As a construction like engineer, remember you need to understand each and every material and their properties. Once you know the properties, then choosing suitable combinations of replacement materials by adopting trial and error technique. What you do here actually? Many of the research I've seen, we are keep on doing the trial and error. That is fine, absolutely fine. If you have one material, two material, absolutely fine. But many times we have faced it, we have thought of it is a very much tedious job. Now, what is the solution actually? Well, the solution is adopt some theory, adopt some concept, that is the particle packing concept. So at this point of time, your knowledge of particle packing concept and its influence on cementitious composite is necessary to enable a mixer designer to select the right proportion of replacement materials from a pool of secondary cementitious materials. So the particle packing of concrete is measured in terms of its packing density. Well, nothing, it is just okay, packing density is the volume of solids by talking about. You know it, we know already in soil mechanics, is the volume of solids divided by the total volume. So how we have to do it actually? Well, what is the basic concept behind this? Well, the basic concept is, now you can see here, this picture is showing all the larger particles. And there is, you can see the white, okay, the gaps is substantial, okay, amount of pores. Now, if you come here, within the larger particles, there are some smaller particles are being filled. So what we tried actually by filling smaller particles? We try to reduce the porosity, the pores. Again, okay, in this picture, if you come here, in this picture, again between the smaller particles, further smaller particles were adapted. Or you mixed a particle size, then a smaller particle size, again, okay, further smaller particle size. So that is the way you minimized the porosity and increased the packing density of the matrix. And that is what I need. As a civil engineer, I need a better packing density and a minimized porosity. Okay, remember, for a civil engineer, the pores which is the culprit, which is the enemy for us. So if you minimize the pores, then definitely people will definitely give a lot of value. So when I see the particle packing concepts, well, there are a number of particle packing concepts are available in the literature, but one which is most found to be suiting for us is the modified Anderson and Anderson model. Is found to be one of the appropriate and best known packing models for cementitious composites. So, well, this formula is from Anderson and Anderson. So there are, okay, like, it is a cumulative percentage final, D is particle size, is minimum particle size, capital D is maximum particle size, Q distribution exponent. Well, if you go into this equation, well, this equation can easily be like simplified in Excel, Microsoft Excel. It is nothing okay great actually. So you have to like understand the concept and you can solve it in Excel. Otherwise, there is a software which is already developed and available, okay, and can be used to fit the modified Anderson and Anderson model. So the key here is the utilization of secondary cementitious materials in conjunction with nanosilica as a binary, ternary, and quaternary blends in cement composite is very much essential to counterbalance the effects of secondary cementitious materials and nanosilica to obtain a high performance sustainable cementitious composites. Well, I just forgot to tell you, even though we are very much efficient in dealing with the secondary cementitious materials, but we know they have certain, okay, properties which are lacking, okay, which are underperforming, okay, than the ordinary Portland cement. For example, the initial strength gain. The initial strength, okay. So when we use fly ash or any kind of secondary cement materials, most of the cases we see the initial strength is to be very, very less, isn't it? Also, there are some other properties or other problems like the setting, okay. So what actually like nanoparticles will do is going to balance the disadvantage of secondary cementitious materials. In same way, the secondary cementitious materials is going to balance the disadvantage of nanosilica. For example, the shrinkage. So when I'm adding a secondary cementitious materials, I may get, okay, better performance with respect to shrinkage. Then one more is the heat of hydration. So when if we use only nanosilica, okay, 4%, 5% or 6%, it is difficult, okay, for me to work with the matrix because the heat of hydration is going to be very high. So what I will do, I'm going to use the secondary cementitious materials, some proportion of secondary cementitious materials, which will help me in reducing the heat of hydration. And we know very well when I add secondary cementitious materials, the heat of liberation of it is lesser as compared to the OPC. So means what we are doing actually, we are just preparing a blended mix, which will have OPC, which will have fly ash, which will have nanosilica. Now remember, the fly ash or the secondary cementitious materials are in the micron range, that is 10 to the power minus 6 meter. And what is the nanosilica? It is 10 to the minus 9 meter. So now again, there is a possibility you can introduce a material between secondary cementitious materials and also nanosilica. That's why you might have seen people are now selling a material called ultra fine fly ash. Now the normal fly ash particle size is around 30 to 40 micrometer. But when I say ultra fine fly ash, the particle size is around 1 micrometer. Okay, so that is the way it is being sold, and it is very much getting popular. Same thing for GGBS. There is a producer in Goa which are naming them as Alcofine. So it's nothing but is a ultra fine GGBS. Okay. So what is the experimental methodology? Well, this part I will cover it fast. So it is as routine, okay, like other like experimental investigation. These are all your physical properties of OPC, fine aggregate, fly ash, and also the ultrafine fly ash, as I was just telling you. Now, this is the properties. These are my properties of nanoparticles or nanosilica. Actually, we purchased nanosilica in a colloidal format, and these properties are given by the manufacturers. Now you can see here, this is my particle size distribution curve for all the materials. Now this is my colloidal nanosilica, and this one is my sand, and these are all of it in between the particles. You can see here this ultrafine fly ash, single, almost single grain, almost 1 micrometer to goes up to 5 micrometer. Single grain material. Similarly, this is my OPC and this is my fly ash. Yeah, so this is the same thing, an extended version again. So now all the experimental methodology means all my mixed proportions were designed through the particle packing concept and were designed through the modified Andreessen and Anderson model. Remember this. That is the actual key here. Now there was a coefficient, I guess you may be remembering, the Q is 0.3. Now 0.3 designates a medium of a workability. So I have adapted a workability mix of medium, okay, like workable. So that is the way we used one software adopted a software like which when I given the different proportions or the different properties of materials, it given me the what is the proportion or what is the right proportion of the material which will give me the best optimized particle packing or the best packing density. And that is what I want, because the best packing density is going to give me the minimum porosity. And for a civil engineer, I need minimum porosity as possible, because that is going to define my durability properties of the material, service life of my structure, sustainability, okay, of my structure. That's why I need minimum porosity. Now here you can see this is my binary blend. That is, I designate binary blend as the OPC plus fly ash or OPC plus ultrafine fly ash. Now you can see here the proportion. This proportion is distributed as 75 to 25. So 75 is my OPC, 25 is my either fly ash or ultrafine. When I'm going to the ternary blend, well, ternary blend is OPC plus fly ash plus ultrafine fly ash. One combination can be. The next is OPC plus fly ash plus nanosilica. Another is OPC plus ultrafine fly ash plus nanosilica. Now, when I given this combination, the best fit is curve is giving me the best particle packing density, giving me the 75 OPC, 15 is the fly ash, and 10 is the ultrafine fly ash. Then 75 OPC, 23% of fly ash and 2% of nanosilica. Same thing for even 25, 75% OPC, 23% of ultrafine fly ash and 2% of nanosilica. So means I am restricting my nanoparticles to only 2%. Only 2%. That is the key here. So that is the way, like as I was telling you, the mixed recipe for multi-blended mortar mixes also prepared the similar way using particle packing mixture and using MR. This is the software actually you can type it in Google, you will get it. This through this software, you can get the proportion for the mix. Okay. Now for a mortar, binder to sand ratio was fixed for 1:3, and water cement ratio, water binder ratio, I would say, is 0.5. Okay. So that is the way the mix proportions of these are the same. Okay, mix whatever the you've seen here. Okay, Fa25 P means paste, and M for mortar. So these are paste. Okay, so these are the, as per this proportion, these are the values or the amount of the material per meter cube of the mix. Okay. So how, okay, like the mortar specimens were mixed. We did all the work through automatic mortar mixing and follow the guidelines of EN 196. So, and mixes of blended mortars were cast in cubical specimens, that is of size 70.6 millimeter. Cylindrical mortar specimens were cast for rapid chloride and penetration tests. I will just show you the results in the last. Then compacted cube and cylinder specimens to humid condition, then demolded after 24 hours. That is a standard method. Actually, we know it very well. Now for a mortar, what I expected my compressive strength, density, the permeable porosity, and the rapid chloride ion penetration values. Okay. So this is the sequence. Actually, you can see the sequence. This is my automatic mortar mixer, and these are my molds. This is the mold for the RCPT, rapid chloride ion penetration test, and these are the specimens. And you can see the specimens were kept okay in a tub, okay, which is fully submerged, and after certain cooling period that were brought for the compressive strength test, and the same one will be used for the your density, and also for the, you can see here, this is for the test setup for the rapid chloride ion penetration test. Now, next is the paste specimens. Well, paste, same mixes except the sand actually. So again, okay, same mortar mixer, but 196.3. In a mortar, it was 1. This is 3 actually. And what is my expected things like setting time, surface temperature variation during the period of setting, workability, chemical sinkage, and advanced characterization of hydraulic paste chambers. How I did actually, well, you can see here, this is a mold, okay, normally being used for preparation of the homemade chocolates. So we got, okay, this mold, which is basically cylindrical silicon mold. This is silicon mold, and diameter is 4 centimeter. Lower, it's a conical, okay, like lower die is 2.5 and height is 3.5 centimeter. So same, okay, same casting was done. Then they were placed in the complete, okay, like submerged condition. Then, okay, after like second duration, the samples were taken out. Then we stopped the hydration, and then we kept in a desiccator. And whenever the slot was available, we did the advanced filtration techniques. That is for XRD and TGA. Like we will discuss about it, and then scanning electron microscope and energy dispersive spectroscopic analysis we did. So this is the method actually, same of the method actually, like, and you can see this is for setting time. This is the like, infrared thermometer for measuring the surface temperature, and this is the flow values, and this one is for the chemical synthesis. Okay, and how advanced like characterization techniques were used? Well, first foremost techniques that is being used is the thermogravimetric analysis, or the TGTTA. So how we did actually? Well, samples were heated to a temperature of range of 50 to 900 degrees centigrade in a nitrogen per atmosphere at the heating rate of 10 degrees centigrade per minute and purge rate of 20 milliliter per minute. So that is the way. Now, if you do like this, what are you going to get? Well, we know it, calcium hydroxide that is weight loss happens between the temperature range of 400 to 500 degrees centigrade. And if you see, there are certain mathematical equations are available. If you do TGA and isolate only the mass loss from 400 to 500, then you can able to get what is the amount of calcium hydroxide is formed for your cementitious composite. So that is the way CS percentage is calculated from this formula. Then water associated to hydrogen product except the CS content means basically your calcium silicate hydrate, remember. So that weight loss between 35 to 600 minus the CS content. If you do, you will get the double-H percentage. That is the equation given by Sojan et al. 2013. Then also like the space samples were characterized for the mineralogical composition of hydrated blended cement paste. Then these are the standard like deflection angle and we like from 10 to like 80 and this is the standard like standing rate. Now how we did actually? Well, XRD is going to give you the mineralogical composition based on the intensity of the pitch. And what is the method of analysis? Well, if you do it, you can do it manually, but it's a very tedious. So when we were doing our PhD, we have done a lot of like this kind of analysis manually, but now it is very much easily available through the expert high score plus software. If you have a software expert high score, easily determine or easily analyze what is the intensity of the piece. Then again, same specimens like from the same specimens, some material is sent to scanning electron microscopy. Scanning microscopy is nothing but it is going to give us the morphological characteristics. So what we did actually, we did SEM with ADX, that is energy dispersive spectroscopic analysis. Now what it gives me, it is going to give me the elemental compositions within the boundary. So I will discuss about what is my elemental compositions. Well, these are basically, these are just plotted here just to understand how much my mortar mixes are fitting to the ideal curve of modified Anderson and Anderson. So this is like you can see here all the curves you can see the black one is the ideal one, and all my like what are the proportions I've taken is they are very much fitting, very much fitting, almost closely fitting, I would say, or even closely fitting statistically, I would say, with the ideal curve. So that is the way I can validate, yes, whatever the mix I've taken, which is ideally fitting to the curve that is given by the modified Anderson and Anderson. Then the compressive strength, you can see here like early age 3 and 7 days, like we know, as I was telling you that when I'm going with the fly ash mixes, or the fly ash replacement of the mixes, mostly I will get the lower compressive strength as compared to the contrary mortar. That is natural actually. But if you go towards 28 days, their improvement is much better actually, much better. However, when you come to the ternary blended cement mortar, those that are incorporated with the Nanosilica, even though they are in very much less percentage, you can see the early age strength is increasing at 3 days by 10% and 18% respectively, as compared to the control mortar. Well, what is the reaction can be? Well, Nanosilica particles promoted the early hydration reaction. So can be the nucleation site for KTU information and more okay positive reactivity. And same okay thing for the permeable porosity, like if you determine the permeable porosity for a nano okay, like silica, you can see here for a this like this one is representing the nanosilica, like, and this one okay, like these two curves are much lower okay with time. With time, if you go to the 56 days, your porosity is dropping down to 5%. So that is actually significant. From you can see here, it is almost 15% for a fly ash 25 mix, and it is coming down almost okay, close to 5%. And same thing for the density. And this is the values for the rapid chloride ion penetration test. Now this curves depicts the curing versus the charge passed in coulombs. And the same similar version of like the, because it is just representing a kind of a porosity, okay, how much of the pores are there in the concrete. So it is actually okay, similar way presenting just like permeable porosity. So the mixes which are having nanoparticles, almost okay, they are quite okay, lesser okay as compared to other mixes. But what are the mixes that you design? To the modified understand model, you can see they all are okay, very much less. It is almost okay, 400 to 500 okay, like coulombs, which comes in the category of very low to very low permeability from the ASTM standard. So that you can see actually, if you go to ASTM standard, you can understand like what is the level of charge passing through the specimens. When setting time, well, we know actually when we add fly ash, you can see here, this is the fly ash mix, setting time is increasing. Setting time is increasing like 118 and 160. But if you come to the nanoparticles mixes, means not nanoparticle mix actually, I would say the blended mix consists of fly ash and nanoparticles, or consists of ultrafine fly nanoparticles. It is almost similar. They are almost okay, similar. So that is the what I want. That is the what okay, I need at this point of time. And same okay, kind of situation for a final setting time. So there are reasons I mentioned here, but because there is a shortage of time, I will not read it. You can read it at a point of time. Same thing for the surface temperature. But surface temperature, as you know, when I add nanoparticles, surface temperature is going to increase because of higher heat liberation. So that is the what is the key actually. Now what you can see here, the moment I'm adding fly ash, the temperature is reducing okay, by around 5 degree, 5.2 degree, which is a significant actually. That's why we are recommending fly ash to be used for mass construction sector. That is the reason. But when I'm coming okay with the nanoparticles mixes, like I would say the blended mixes or the ternary blended mixes, you can see here the temperature okay is almost okay close to the control, almost close to the control. Now we have to check actually, and there are some reports also there. Control with only nanoparticles, the temperature will go up to 40 degrees. We have also data is not here, but we have checked. The temperature goes to 40 degrees. But when coming to the blender, well, it is almost okay, similar, okay, almost similar to the control mix. Okay. So this is my again workability. This is my workability. So I will tell you, like the moment I have started adding the nanoparticles, we are bound to okay use a plasticizer. Otherwise, it's not possible actually to get a workable mix with nanoparticles. But as I was telling you, like in the beginning, see, you can see here that when I'm adding only fly ash, my workability is increasing. My workability is increasing. And that is what okay, like we know very well actually. But the moment I'm going with the nanoparticles, it is slightly reducing. You can see here reducing even though I am using some percentage of plasticizer. Actually, but just okay, because I am showing you because just I tried to match almost close to the control mix, because nowadays is a 100 millimeter slump is a common actually, and we are mostly going to the self-compacting concrete in most of the constructions. Now we go to the chemical shrinkage. Well, chemical shrinkage is a separate method actually. I will tell you. There is a method, as I told you, which is measured through the flask. Measured through the flask. Now you can see here the mix in which I have ultrafine particles and nanoparticles. The blended mix, which like you can see the UN25. You can see here, like after the 14 days, there is no more data. 28 days, 56 data is not there. Means there is some problem. Problem in the sense the shrinkage associated to the chemical reaction. Associated to the chemical reaction is going to too much. Is going to too much, and that is the where I am getting the volume expansion. So, so when volume expansion happens, what happens? Now you can see here. You can see here. Here, see, you can see these are my set of like flask with different combination of materials. When I'm going with the, when I'm observing okay, the chemical shrinkage for a mix which contains the ultrafine material also as well as a nanomaterial. Now I'm getting a crack here. I'm getting a crack here, and you cannot believe. One day, like I see my student came and reported, sir, all the waters have leaked out because of the crack formation in the flask. So that is what is going to be challenging for me. So means shrinkage is unavoidable when you use nanoparticles. So what is the key actually? Well, the key here is more and more curing. For a solution for shrinkages, I will tell you the curing. Okay. So let us move into the advanced characterization, that is your thermodynamic analysis. Well, if you any one of you like know like TGA, but we normally civil engineers like are not much comfortable with the thermodynamic analysis. Now, what is the like research is saying? The research is saying significant weight loss found with the temperature ranges of 110 to 400. If it is happening, I would understand it is dehydration of water molecules associated to calcium hydrate. So means my like formation of calcium silicate hydrate. If there is weight loss in the process of thermogravimetric analysis, I would say that is my calcium silicate hydrate, because that is where dehydration of water molecules happen. Between 400 to 500, it is dehydroxylation of calcium hydroxide. And beyond 600 to 800, it is decarbonation of calcium carbonate. Well, in this presentation, I am not discussing about the calcium carbonate, but we discuss about both the CSH and CH. So the clear identification of temperature boundaries is provided from the derivative thermogravimetric curve. So you can see here, now this is my TGA, that is thermogravimetric analysis. When I'm going to the DTG, that is derivative of thermogravimetric analysis, the same curve, okay, you can see here, it is going to give me the peaks. And these peaks are nothing but your change in loss of mass. And there is clear, distinct peaks in the cementitious composite when I'm doing TGA. So you need to understand this peak has a significance. This peak, second peak, another significance. So each peak has some significance, but you have to understand what is that corresponds to. So I realized this is nothing but my CSS, and this is nothing but my CX, and this is nothing but my calcium carbonate. So, so that is where I will identify or I will understand what is my proportion of CSH in my cementitious composite. Now, if you see here, like whatever I like, the equation I like told you in the some couple of slides before. If you follow that equation, you can determine the amount of calcium hydroxide in your mix. Now you can see here 7 days and 28 days. So as you know, in the beginning, beginning of your hydration process, definitely your calcium hydroxide will be started forming, and 28 days we are adapting or you are assuming, suppose, okay, yes, that is the hydration of almost is getting over, or some percentage, significant percentage getting over, then I will say, like, for a control, okay, paste is the highest percentage of calcium hydroxide. So that what it will corresponds? Well, that will correspond to more, okay, volume of your capillary porosity. Remember. So means if you are, that's why that is the reason using of or usage of OPC is not being preferred, because that is going to give me the largest capillary porosity. Now, what is the capillary porosity responsible for? Remember, it is responsible for the seepage. Even though you are in 10th floor of the building, the water will be seeped in, and that is the force of capillary. So what is the what we are understanding? Well, we are understanding the moment I am coming from the going towards binary, the as compared to control, your CH is getting reduced. Same thing, okay, for your 20 days also. Now, when I'm going with the multi-blended, okay, ternary blended, then I see, or I'm having a nanoparticles, I'm drastically reducing the capillary porosity. So you can see here in the 28 days, it is almost 20%, but here it is less than 10%. So that is the way I'm going to increase the durability of my material. Durability of my material. Now, what is doublets? Well, we know doublets is nothing but is the water associated hydration process, or is indirect measurement of calcium silicate hydrates. So you need more CSS or not as a civil engineer? Well, of course, you will say yes. As a civil engineer, I need only calcium silicate hydrate. That is what is defining my engineering properties of the concrete, of the cementitious composite. So you can see here, the moment I'm going to the blended of nanoparticles, you can the calcium silicate hydration formation is much more, okay, as compared to the control and the fly-ash and binary blended mixes. Binary blended mixes. And that is what is Nanosilica can do if you can really, okay, handle it. Same thing for the mineralogical, I will not take much time, okay, just another 5-10 minutes. The mineralogical composition, when I'm going with the XRD, the XR diffraction, I am getting more prominent peaks for calcium silicate hydrate when I'm going with the nanoparticle admixed concrete or nanoparticle admixed cementitious composite. You can see here, now this is the what, okay, you can see the peaks are too much here as compared to the control mix. The peaks are very much less. So the intensity of peaks is going to define you how much your material has reacted, how much your material has reacted and form the calcium silicate hydrates or form the hydration products. So that is what we are going to give you from the example. Next, moving to the scanning electron microscope. Well, these are all images are secondary electron images. So I should not say much confidently, but I can say that when I'm going from control to the fly ash, from fly ash to the ultrafine fly ash, and ultrafine fly ash to the nanoparticles, my matrix is getting only denser and denser. Except that I cannot tell much because this is a secondary electron image mode. But what I did actually, you can see here that these are the squares in each and every figure. And when I am going with the energy dispersive spectroscopy to understand the elemental compositions. So if you go and do some elemental composition, you will get an element analysis like this. And what is important for me, for a civil engineer, important for me is the calcium and the silica. The calcium and the silica. So the calcium by silica ratio is going to define how much my material is hydrated. Suppose you are getting a Ca by Si is more, means calcium is more and silica is less. Means what will get? More calcium is there means definitely there is some unreacted cement. So calcium is could not able to react with silica and could not form the hydration products. So that is my understanding actually. If it is less, you will say confidently yes. So my calcium is completely consumed and reacted with silica and form the required hydration products. Okay. So if you compare, like for all the mixes of like this kind of, for all the mixes, this kind of analysis were done. And then this Ca by Si ratio, if you now understand, you can see that from the control, when I'm going to the binary, from binary I'm going to ternary, Ca by ratio is reducing down, reducing down, reducing down. So means that is good for me, actually. That is benefit for me, actually. So, so more values, more values I'm getting in case of it. Ternary blended mixes. So if I'm going to the conclusions, like implementing the theory of particle packing is given me a beautiful idea about understanding or defining the proportions of the mixes. Then when I talk about the LH properties like setting time, surface temperature, and flow properties were tailored with the combination of micron size SEMs and nanosilica. TGA, from the TGA analysis, like what I can understand, like when I'm going with the blended, cementitious composite integrated with nanosilica and in the presence of supplementary cementitious materials, it has a tremendous potential in reducing the calcium hydroxide. And it is producing more calcium hydrate. And that is what is going to define my concrete as more durable. Same thing, like for a mineralogical composition, like ternary blended cements is showing the significant peaks, and that is you can say my CSS formation is much better. And from Ca by Si ratio, like through SEM index, I can conclude that lesser Ca by Si ratio is forming for ternary blended nanosilica mixes for all ages. So that indicates the formation of calcium hydroxide is more and more denser, and particle packing density is much compared to the control mortar. So that is the way the nanosilica integration, even though in a small scale, even though in a small percentage, but keeping the secondary cementitious material at a large percentage, making my cement or making my cementitious composite more sustainable, as well as high performance, because I see there are formation of hydration products. So that is the way I can conclude, like I can able to produce a sustainable cementitious composite by integrating secondary cementitious materials as well as nanosilika. So these are the publications you can see. Like if you want, okay, like still there are some more publications, but I listed just some important publications. And thank you one and all. Like if you have any questions, I can really take some of the questions.
Thank you, sir. Thank you so much for the informative talk.
Thank you so much.
I hope all the participants have benefited a lot from this session. E-certificate will be provided to all participants. For that, I request all the participants to fill the feedback form available in the chat box. Now the forum is open for question and answering sessions. Participants can unmute and ask their queries, or type their queries in the chat box. Since we have some questions in the chat box, shall we start?
Okay. Can I read the?
No, I'll read it. I'll read it for you,
yeah.
sir. I'll read it for you.
Yeah.
So the first question is there RMC units producing concrete utilizing these, and whether standards available in courts?
Well, that is a really good thing. I want to like take this material to the RMC. Okay, but you know, like if you estimate, okay, the cost of this concrete is right now is very high. As I was telling you, the nanoparticles, which is one of the costly material, is making the overall production of the concrete is very high. So at this point, if you go to any RMC, there are many RMCs are there, like thousands of RMCs are there. They have come to the level of ultrafine materials, which is of range of 1 micrometer. But till now, unless there is some specialized applications, RMCs are not using nanoparticles because it is very costly, and there is no buyers for this kind of concretes. Okay, so that's what I'm still telling you. It is still in the research stage, and we have to make it, bring it to the practice.
Okay, sir.
Is that
fine? Yes, sir. So the second question is, can this blended cement mortar is used for all type of climatic conditions?
Absolutely. Okay. So see, it can be used for all kind of climate conditions. See, we know, like particularly for India, like I would say there are two climatic conditions. One is the coastal, like it starts from the Bay of Bengal, like West Bengal, and comes to Odisha and Andhra Pradesh, like all East coast, then southern coast, and then west. So till Gujarat, you can say this all has a one climatic conditions. The structures which are near to the sea, certain distance from the sea. Now you have to prevent your structures from corrosion. That is one, and the rest of India is another climate. So there is no problem of corrosion. Like for example, you go to Delhi and all, like central, like Bangalore and all, we have no problem of corrosion. Severe problem of corrosion. So you have to safeguard only with respect to your durability conditions, and that's what is your microstructure. And whatever I spoke about, blended cementitious composite can be used for all climatic conditions. See, remember the porosity, minimizing the porosity and increasing the particle packing density is the key for us. So irrespective of the climatic conditions. Okay?
Okay, sir. Okay. The third question is, can you suggest some projects for undergraduate students related to this topic?
Well, it is, I think it is okay. It is all of your job, like to go into this topic. And if you're really interested, see, undergraduates can define some new topic, which I will tell you. So absolutely yes, you can give it to undergraduates. May not be on a full scale experimental, but you can give a little bit on the, and they will really definitely want us. Okay.
Okay. Thank you, sir. I think there are no more queries in the chat box.
Okay, so I really would like to thank each and everyone, okay, for the patience you learned, okay. If you have any questions at any time, okay, like you can really, okay, be in touch with me through my email. That is, I have a NITK email ID, like that is bdas@nitk.edu.in. So you can contact me at any point of time, and I'm going to answer you positively. Thank you, thank you, madam. Okay, thank you so much.
So now I would like to invite Dr. Smita KK, Associate Professor, Tockage Institute of Technology and Science, to give a feedback on this session. Ma'am, please. Smita, ma'am. Ma'am, are you there? I think she's not in the meeting. Ma'am, can you please respond? Okay, I think she's not there. So any of the participants can also feedback if anyone is interested. Any of the participants kindly give a feedback. Okay, we will admit her. She's there. Okay, we will admit you, ma'am. There is some technical issues. We will wait for. Yes, ma'am, you are audible. Your video is on. No, you are not audible, but your video is on.
Well, madam, I think it is fine. Okay, don't worry about the about the feedback. I think you have given already a link. Okay, I can see in the chat box. So they are going to give you the feedback. Give the feedback about the session. So and any time, anywhere, okay, like any doubts are there, I will be happy to assist anyway. Okay. So with your permission, if you allow me, I would like to leave. Can I leave actually?
Yes, sir, you can, sir, you can.
Yeah.
Thank you so much. Thank you so
Thank
much
you.
for being here, sir.
Thank you so much. Thank you. Thank you. Yeah. See you. See you. Bye.
See you.
So that's all for the second session. Now we will have a lunch break, and I request all the participants to join through the same link for the afternoon session at 2 p.m. And a reminder for the participants, as I already said, we are conducting a Google quiz. So kindly participate in that quiz. The link will be shared to your WhatsApp group. Top scorer will get a cash prize of ₹1,000. Thank you.